This is General Physics 2, Week 10, AC. I want to work a quick example. This is part 4 in the videos. The first video was 1 through 3. And here I want to work an example hooking up an AC light bulb. So let's imagine that we've got an AC light bulb that's designed for 120 volts AC. So here's going to be my AC source. We'll hook it up to 120 volts AC. That's just what you get out of the wall. And so then we'll plug in this light bulb. It's going to be an old style incandescent light bulb that is 60 watts. So it's got 60 watts of power, and it's meant for 120 volts AC. That's the same thing as 120 volts RMS. Volts AC is the same thing as volts RMS. When we hook this up to an AC waveform, like the power that comes into our homes, the waveform looks something like this. And there's a peak value, a V peak, or a V maximum, you could say it either way. And then there's an RMS value that's something less than that, V RMS. And the relationship between those for a sine wave is 1 over the square root of 2. V RMS is 1 over the square root of 2 of V peak. It's about 0.7. Now what I'd like to do is, with this situation, see if we can calculate everything that we might want to know about this. What's the maximum voltage? What's the RMS voltage? What's the maximum current? The RMS current? That sort of thing. So let's make a little chart here. V max, I max, these could be called peak just as easily. And the power max, there's going to be peaks in the power. What are those values? And then over here I'll put the same thing for the RMS. The VRMS and IRMS, and the corresponding power is the average power. So these are the things we'd like to know. This is our situation. Now take a moment to think. There are a few of these that you just plug in directly. Do you see which they are? Which are the things that we already know from this situation? We've plugged it into 120 volts AC, and it's a 60 watt bulb. Which things do we know already? Okay. VRMS, RMS is the same thing as AC, so that is just 120 volts. That's what we have there. The RMS voltage is 120 volts. IRMS we don't know. This 60 watts, that is the average power. So that is one thing we know. Now, what can we calculate from this? What can we figure out? Well, let's start by seeing if we can figure out IRMS. And maybe you can remember a relationship. Power normally is current times voltage. But what about in this RMS world? Well, it still works. That is the trick. Using RMS, the same formulas work. So we can just say that the average power equals IRMS times VRMS. So if we put that in, we would have 60 watts equals IRMS times 120 volts. And I think you can figure out what IRMS must be. It surely is 0.5 amps, that would be. So now we've got an answer to one of these, and that is this IRMS is 0.5 amps. Now what about these maximum or peak values? If we know the RMS value, can we get the peak value? Well, I've already told you the relationship for a sine wave is that VRMS is 1 over the square root of 2 times V max, or V peak. But you can just turn that around and say then V max must equal the square root of 2 times V RMS. So that's the square root of 2 times 120 volts. And that is equal to about 170 volts. It's just a smidgen less. We'll round it off to that value for now. And IRMS we can figure out, well, to get I max, we can use the same relationship. IRMS is 1 over the square root of 2 times I max. But that just means that I max is the square root of 2 times IRMS. To help you remember which way these things go, just remember the RMS value is smaller. The peak is the top, and the RMS is something less. So if you've got the RMS and you're trying to find the peak, multiply by the square root of 2. That's 1.4. It's going to be a larger number. Multiplying this by 0.5, what we get here is 0.707 amps. And what about the maximum power? So remember, the power goes through these peaks. When the voltage is at its peak, that's when the current is also at its peak, and that's when the power will be at its peak. And then when they all come down to 0, there's no power. And then on the negative swing, voltage is negative, current is also negative, the power is still positive. And so you reach the same peak again. But how do those peaks relate to the average value? Well, one could compute this a bunch of different ways. Let's just guess that the maximum power should surely be the maximum current times the maximum voltage, or the peak current times the peak voltage. And we've gotten values, I should have put them in here. We've gotten 170 volts for the maximum voltage and 0.707 amps for the maximum current. So we could take 0.707 and multiply it by 170 volts, and we would get exactly 120 watts. Now, isn't that interesting? That's exactly double 60 watts. Exactly double 60 watts. So, but that's what we said before when I was looking at the power curve and how it wobbles back and forth between the peak and 0, and its average value is exactly half the peak. So here we have the average power is 60 watts and the peak is 120 watts. That's just what you'd expect. One last question. What DC voltage could we use? If we wanted to operate this bulb from DC instead of AC, what DC voltage could we use to get the same brightness or the same power from the bulb? That's the question. What DC voltage should we use? Should it be the peak voltage? Should it be some other value? Well, if you think about the peak voltage, you'd say if you put a DC value like that, then it would be putting out that peak amount all the time. That'd be too much, clearly. So it should be something less, but it's not exactly clear, maybe. What particular value? Well, let's see if we can figure this out. What we ought to do is figure out what is the resistance of the bulb, and then I should put this one in here too. What's the resistance of the bulb? And then we can figure out what voltage to apply to it to get the same power. How would you figure out the resistance of a bulb like this? Well, usually you'd say R is V divided by I. But which V and which I? Well, these formulas, again, they work. Just like we used this formula up here, that's the same formula we had before, but we were using RMS values. We can do the same thing here. You can put the RMS values in here, and it still works. It works exactly right. You could also put the peak values in. It works either way in this case. But let's put in the RMS values. So we would have 120 volts, and IRMS is 0.5 amps, and that would give us 240 ohms. So that's the resistance of the bulb. Now, with that resistance, can we figure out what voltage we should apply to it if we were using DC instead? So the idea is you want to come along with a DC voltage and with a known resistance of 240 ohms, try to get the right amount of power coming out of it. So we need a relationship between power, 60 watts, and resistance, and voltage. Voltage is what we're trying to find. So remember the formulas for power. Power is current times voltage, or it can be V squared over R if there's a resistor involved, or it can be I squared times R. So what relates power and resistance and voltage? Why, it's this one right here. So let me write it again. Power is V squared over R. We want to solve this for V. So solve that for V, and what would you have? V is going to be a square root, and it's P times R. Well, let's put the numbers in. P, the power, is 60 watts, and the resistance we just calculated was 240 ohms. If you take the square root of 60 times 240, you will get exactly 120 volts. So the answer is 120 volts. So the DC voltage you should use to get the same power from the bulb is exactly the same as the AC RMS voltage. That is the right value to apply if you want to use DC instead.